Now let's go to these tricks that I want to talk about. So I would say that for parallel, these are important parallel resistor tricks. And what you're going to find here is there are two tricks that could significantly help with calculations. So here we go. So the first of the two, I'm going to call the two parallel resistor trick. So we know how we have defined parallel resistance. So the usual way of calculating the parallel resistance is not efficient. Okay, it's not efficient. So typically what we do here is that we then say, okay, our parallel is this. And then we just start adding things like this. So what we want to do here, and by the way, a lot of textbooks encourage you to do this. So what I'm going to say is that here is a more efficient way. Now, I don't want to call it Carlos's way because somebody else showed me how to do this. So here's a more efficient way where one focuses on two resistors. And so mathematically, what happens if you focus on two resistors? Well, if I have two resistors, R1, and this is R2, the way we calculate parallel resistance is we do what? We say that 1 over R parallel, that's going to be 1 over R1 plus 1 over R2. But if we solve for R parallel, we could then read that R parallel reads like this. It's going to be R1 and R2 divided into R1 times R2. I would say that this is a very powerful relationship. A very powerful relationship. And this is what we want to focus on. You can multiply both resistors and divide by the sum. That's the power of this relationship. Now, what you want to find here, or what you want to think about it, is that the pattern I will show you here is useful because textbooks problems use nice values for resistors. And as a consequence, you can apply a pattern that's really useful. So let's check it out. So the first thing you want to do is that let's start looking at values. So let's say that we have R1 is equal to R2. Okay, that's the first pattern we want to look at. So if you look at this thing, then of course I'm going to have two resistors. Again, R1, and in each case, I'm going to have the exact same picture, so I won't draw this again. So the way I write this here is that I'm going to redraw this, and I'm going to call this R1 parallel to R2. Now, if I look at R1 parallel to R2, note that we've already mathematically calculated up here above. So then this becomes R1, R2, R1 plus R2. But wait a minute. We know that R1 and R2 are the same. So what I'm going to do here is I'm going to replace R1 with R2. So if I do that, I automatically get R2 times R2 divided by R2 plus R2. And you could see that it becomes 1/2 the value of R2. So for example, imagine that I have two resistors that are 12 ohms. I then take the R2 value and I multiply it by 1/2. So instantly, I could say that this is a 6 ohm resistor. That's the pattern. So here we go. Now, let's see what happens now. What happens if I have R1 is equal to 1/2 R2? And the thing that's really important here, you must pick R2 to be the larger value. That's the cost. So now, here I go. I have R1. So if I play the same game now, I have R1 parallel to R2. Look what happens. Now I'm going to convert R1 into R2. So then this tells me again, I'm going to do this one more time, and then I'm going to stop. So now if I place R1 in here, note that this is 1/2 R2 times R2 divided by 1/2 R2 plus R2. So if you calculate this thing, this becomes a third value of R2. So now let's start looking at the pattern. If they're a 1-to-1 ratio, then I divide by 2. If I have R1 half the value, I divide by 3. So a nice example would be something like this. Let's say that I have a resistor that we have a 6 ohm parallel to a 12. Since 6 is half of 12, I can immediately say that I'm going to take a third of 12, which then automatically gives me a 4 ohm. So by inspection, I could tell you what that resistor value is. But let's keep moving. Now I'm going to pick a value which is 1/3 the value of R2. So I played the same game. So I'm going to go R1, 2. Now look what I'm going to do. I'm going to replace R1 with 1/3. So then I'm going to get 1/3 R2 times R2 divided by 1/3 R2 plus R2. And when I compute that, look what I get. I get a 1/4 of R2. So you could start to see the pattern here. A third, I divide by a 1/4 for the larger value. Here's another example that we can do. What if I have a 3 ohm in parallel with a 12? You could see that the 3 ohm is actually a third of the resistor value. So what do? Wait. not 3, it's 4. Fourth is a third of the resistor value. So then what am I going to do? I'm going to take my 12 ohm resistor and I'm going to multiply that by 1/4, and that's going to be 12, and this is going to be 3 ohms. So you probably get the pattern now. So if I get the pattern, you could see that if I go to the next one, what if I choose R1 equal to 1/4 times R2? Right away, that tells us then, without doing any more algebra, that this must be 1/5 R2. And I keep going on. And I on and on and on and on and on, and you could now see what the pattern is. That is really powerful. So you can quickly reduce resistors in circuits because of this reason here. Now, let's go in and look at the second trick. And this is what I call the CDR trick. So the CDR trick requires us to focus on 2 resistors, okay? So we want to focus on 2 resistor branches. Even though I may have 4 or 5, I'm going to only focus on 2. So when I think about my circuit, I'm really talking about, here's my branch, and then I'm going to have 2 resistors here. I'm going to have R1, and I'm going to have R2. And so when I look at these, I'm imagining that I have a current I1 coming down, and I have another current coming down, which I'll call I2. So the only thing that I need here is that I'm going to have a current that this will be I branch. Okay, so here we go. Now using the trick up above here, which is this parallel relationship, it makes life a lot easier. So here we go. Apply CDR to get I1 and I2. So here I go. I1 now reads what? It reads R parallel over R1 times the branch current. So look what happens. If I put in the actual values for R parallel, I have R1. Now I have the combination of R1, R2 added times R1, R2, and then I get I branch. The first thing that you note here is that note that there is a cancellation between this R1 and that R1. So in other words, I get R1 plus R2 into R2 I branch. And this here is going to give me my current I1. Let's repeat the process for I2. So if I do I2, you're going to see here is that again, I have R parallel divided by R2 this time. And so if I repeat this exact same process, you see here is that this time the R2s cancel out. And what I'm left with is that I get R1 plus R2, but this time into R1. And this tells me what the current I2 is. Check this out. I could immediately I could reduce the current divider rule that it reads like this here. That as the resistances go, so the current I1 is the opposite resistor value divided by the sum of the two resistors. So if I want I2, it's going to be the opposite resistor of resistor 2, which is then going to be R2 divided by the sum of the two resistors times the branch current gives you the current. So as an example, let me show you how this works. So here, what we want to do here is that we want to calculate the resistor currents. And let's say that I have this circuit, which is going to be 6 amps. And then I'm going to pick resistors that read, this guy is going to be a 6 ohm. This will be a 4 ohm. And then this one will be a 12 ohm. So you can see here is that I'm going to have 3 currents. I'm going to have the current I6. I'm going to have the current I4. And I'm going to have the current I12. So I want to calculate these. So let's calculate current 6. So what I do in this situation, what I want to do here is that I want to now calculate I6. So the first thing that we do here is that we reduce this circuit. So we immediately reduce this. So if we reduce this, this tells us that this will be 4 parallel to 12. That's a third. So then I divide the highest resistor by 4, which then gives me a 3 ohm. So then if I go back to my circuit, I now know that this is 6 ohm. And now I know that this is an equivalent 3 ohm resistor. So I'm only interested in calculating the current I6 right now. So now I apply CDR. So if I apply CDR, CDR then says that the current of the 6 ohm is the opposite resistor, which is 3, divided by the sum of the two resistors, times the branch current, which is 6 amps, and that gives me immediately 2 amps. And you can see here that that is very powerful, how I could take 3 resistors and only focus on one. So if I look at this thing, we can keep playing the same game. So now, how about if I copy this and bring this down? Oops. And I want to redraw the circuit with the new current. And what I mean here is newly calculated. So when I paste this guy in, look what I'm seeing here. I know that I have 6 amps is coming this way. I now know that along this branch right here, I have 2 amps. So what does that mean? that means here is that I have a current, according to KCL, I have a current that's 4 amps going to the right. But note, I see two currents though. I have two resistors in parallel. So because the current has been divided so that the two branches now see 4 amps, I'm going to apply CDR. So now apply CDR to get I4 ohm and I6 ohm. So then I4 ohm is going to be what? It's going to be the opposite resistor. So it's going to be 12, but then it's got to be divided by the sum of the two times now the branch current, which is 4 amps. So this immediately gives me 3 amps for I4. So right away, I can compute that very, very efficiently. If I look at the current I12 then is the opposite resistance divided by the sum, and this time it's going to be, no, it's going to be 4, not 12, times 4 amps, and then I'm going to get a value that reads 1 amp, which is I12 ohm. Very powerful trick.